Hi, and welcome to this talk on techniques for observing through satellite interference. I'm Steve Ellingson from Virginia Tech, and this work is resulting from a collaboration between me and Mike Buehrer, who is also from Virginia Tech. Interference from satellites afflicting radio astronomy is a problem with a long history, which I will not attempt to recount here. Suffice it to say that the problem with satellites is that radio telescopes cannot hide from them. There is no place that's sufficiently remote to avoid them, and the numbers of satellites continue to grow. It's important first, I think, to identify the traditional ways of dealing with satellites. First is, of course, spectrum management and regulation, and that's essential to be sure. Inevitably, interference remains, however, and then comes avoidance. You don't point at satellites, and you don't observe when they're trouncing across your side lobes. Also, maybe the satellite operator will agree to turn down the power or repoint the beam as they're passing overhead. Also a form of avoidance is filtering. This is often effective, but you lose some access to spectrum and probably also significantly increase the system temperature, which of course degrades sensitivity. So filtering is really a double whammy. It's losing access to spectrum and degrading sensitivity in the remaining passband at the same time. Of course, there's also data editing. Take the time-frequency plane, break it up into little pixels of time and frequency, and dispose of the pixels that contain interference. This is often very effective, but also not without problems. Key among those is that you're still losing access to spectrum. Then we consider the non-traditional, you might say experimental approaches. The ones that come to mind right away are spatial nulling, which is possible when you're lucky enough to be using a large array of some sort, and time-domain canceling, and we'll come back to that one. Also, I call these non-traditional because, to the best of my knowledge, none of these are in regular use. I'll address some reasons for that in a moment. What this talk is about is taking another look at non-traditional methods, with the goal being to observe in spectrum that is being occupied by satellite transmissions. Why? Well, the satellite RFI situation is changing. The prospect of multiple constellations of low Earth orbiting satellites, with each constellation having tens of thousands of satellites, means that we are approaching an era in which there will rarely be a time when there are no satellites overhead, and often likely there will be multiple satellites overhead at once. And that does not bode well for avoidance-based strategies. So, is there a plausible way to observe in the presence of satellites? And by that I mean looking through satellite signals and not merely avoiding them. Given that the answer to that question is probably not going to be an unqualified yes, well, at least not always, then the question is, to what extent is coexistence possible? I don't know the answer to that, but an answer to that question is what this project is working toward. If there's good news, it's that satellite RFI has some features which make it much easier to deal with than terrestrial RFI. One is that satellite signals are received through propagation channels that are very simple, with predictable Doppler and near-zero delay spread. The way to exploit that is through coherent time-domain canceling. CTC is the abbreviation I'll use here. There's a particular CTC architecture which I think is very well suited for this, and that architecture is shown here. Basically, you compare the incoming signal, x of t, to a reference signal, d of t, and that reference signal d of t represents the best available information that you have about the interference. The result of that comparison is an estimate of the interference waveform, and you subtract that from the input. This is feed-forward architecture because the output of the canceller depends only on inputs and does not depend on past output. We've spent a lot of time on this approach recently, and you can read all about it in the paper cited below the figure, and which I'll refer to many times in this talk. The reference signal d of t can come from one of two sources. One is from an auxiliary antenna of some sort, preferably one that is better at receiving the satellite than the astronomy. The other possibility is a mathematical model of the signal, in which case the canceller's primary task is to solve for the parameters of the signal model. And, of course, there are hybrid combinations of these two sources. For what I'm talking about today, the specific details of how we get the reference signal will not be important. The only thing that will be important is that we can identify an interference to noise ratio for the signal. The other property of satellite signals which can be exploited is that they have predictable direction of arrival, and they arrive with essentially zero angle spread. This makes us want to try to put a spatial null on the satellite, and why not? If you just think about big dishes for a moment, then null forming traditionally means that you need a phased array feed. And that's totally doable, but not without introducing some troubles. One of these troubles is that null forming using phased array feeds inevitably means some distortion of the pattern, and also some variation of the main lobe gain, and that's obviously troublesome for radio astronomy. The alternative that we've been looking at is an electronically reconfigurable surface, essentially a reflect array that passively modifies the scattering from the rim of the reflector. As I'll show later, this lets you do some amazing things, including null forming, and it can do this without significantly perturbing the main lobe. So these are the two things I want to talk a little bit about today. A little background on CTC. Some of you may know or remember that there was a lot of excitement about this idea about 20 years ago. It was clear then that one of the attractive use cases would be satellite RFI, and there were some encouraging initial results. I'm showing two of those here. At the top of this slide is work I did with AT&F folks on canceling GLONASS at the ATCA. This was using parametric waveform estimation for the reference signal. After a bit of fiddling around, it worked quite well, as shown here. At about the same time, Carl Warnick's group at BYU also went after GLONASS at the GBT. They used the reference antenna approach and also, again after some fiddling around, got a nice result. So again, proof of concept achieved. There were certainly other attempts and other successes, but one thing that was troubling was that we had only the vaguest idea about how to predict the results, so that designing algorithms and deciding things like filter length was basically trial and error. That issue becomes important a bit later in this talk. Of course, after these initial proof of concept successes, interest in this stuff dwindled. And that's understandable. It was complicated and it was hard to implement. And there were toxicity concerns. We found conditions under which interference would be canceled, but the spectrum could be corrupted in one way or the other. We understand that better now, but I think the opinion lingers that maybe this capability is not really worth the trouble. But, as I pointed out on the first slide, that situation may be changing. So far I've been vague about the algorithms, and that's simply for brevity. The details are in the paper. However, I do feel compelled to say something about the algorithms. Our focus is on a strategy commonly known, at least among signal processing theorists, as MMSE, which stands for minimum mean square error. It's simply a method for calculating a filter which minimizes the mean square error between the filtered reference signal and the input interference. The two things that are important to know about MMSE is that, well, one, it's optimal, and two, it's computationally expensive. We're also considering a reduced complexity version of MMSE that's obtained by making certain assumptions about the structure of the propagation channel, namely those that I mentioned earlier. When those assumptions are valid, and they often are, then the reduced complexity MMSE algorithm works at least as well as proper MMSE, and you get a huge reduction in computational burden. Again, full details in the PASP paper. I also want to make a distinction between feed-forward MMSE and other algorithms that show up in this business. In particular, many folks have heard of LMS, that is least mean squares, and also RLS, which is recursive least squares. These algorithms do similar things, but they are intrinsically feedback algorithms. That is, the output depends on past output and not merely on input. They generally have reduced computational burden, but you pay for that with some additional squirrely behavior. My opinion is that for this work, LMS and RLS are strongly contraindicated, and the reduction in computational burden is not really an issue. So, how does one go about evaluating a canceller? Generally, the metric you would use is some version of what I'm showing here, and I'm calling this interference rejection ratio, or IRR. In plain English, IRR is the power of the interferer at the input divided by the power of the interferer at the output. And that should be simple enough, except there are multiple ways that you can measure interference power at the output. One way is to consider only what the canceller did to the interference, and that gives you what we call IRR sub 1 in the upper left. Another way to do this is just to treat the signal that comes out of the waveform estimation filter as the interference estimate. And this is not the same thing as what we're measuring in IRR1. Instead, this is what we call IRR2, as indicated in the lower left. Now, IRR2 conflates interference with other things that end up going through the filter, including noise. Nevertheless, it's a totally valid way of measuring canceling performance because the canceller is presenting that additional stuff as part of its interference estimate. So, long story short, IRR1 and IRR2 are both valid and useful metrics. And here's a takeaway point, these two metrics are frequently conflated in the literature. And this has caused some confusion because the difference is significant, as you'll see in a moment. If we want to do a performance study, then what we need to know is IRR as a function of a few things. Certainly, the interference to noise ratio at the input, which I'm calling INRX, is important. Also, interference to noise ratio of the reference signal, which I'm calling INRD, is also important. As far as design, there are two considerations. First, the amount of data that's used to design the filter, and we'll call that L. And second is the length of the filter, and we'll call that M. And here's something that comes as a pleasant surprise. Quite often, it turns out that the optimal value of M is 1. That is, the filter consists of merely changing the gain and phase of the reference signal. Again, more information about that in the PASP paper. Finally, the fractional bandwidth of the signal can be important. To account for this, we usually study the extreme cases. That is, well, first, signals which are narrowband in the sense that they cannot be spectrally resolved given L and the sample rate. And at the other extreme, signals that are wideband in the sense that they fill the entire Nyquist bandwidth. These are the two extremes. After some formidable mathematics, you can work out the expected values of IRR1 and IRR2 as a function of INRX, INRD, L, and M. And here are those expressions. I'm not aware that these expressions have previously been published, which is surprising because they're pretty useful. Now, I need to point out that these expressions are specifically for the narrowband interference case, and the expressions for the full band interference are slightly different. In the interest of time, I'll once again direct you to the paper for the full story. Here are the results for IRR1 plotted as a function of reference signal INR. The colors indicate different values of input INR. The markers are the results from simulations, and fortunately the agreement is very good. The key thing to note here is that there are two domains of performance, and where you want to be is on the right of this plot, where the IRR is independent of reference signal INR. Since we have the expressions, we can also work out the appropriate values of L, that is the amount of data to use when designing the filter. And in this case, it turns out to be pretty simple. If you want to bury the interference by a factor of 10 in terms of the power spectral density of the post-observation noise, then you need to calculate the filter using a number of Nyquist rate samples equal to 10 times the square root of bandwidth times integration time. And this kind of thing is really the point of this study. Knowing these functional relationships, you can now start designing this type of canceller using principles as opposed to trial and error. Here's the same result for IRR2, which was the alternative way of defining IRR. If this is your preferred metric, and it might well be, then you see things are a little bit different. The slope on the left is different, and the result on the right now depends on the length of the filter, and not in a good way. Okay, now in the remaining time, I'd like to show you the ERS concept. The idea is to use some fraction of the rim of an existing reflector to implement a reflect array. The reflect array is completely passive. It's just a bunch of patch antennas. But the impedance on the terminals of each patch can be independently adjusted, and that lets you control the scattering. To give you an example, here are some parameters. Here we'll consider a dish having diameter 18 meters, an F over D ratio of 0.4, a simple feed to facilitate the analysis, and we'll use the outer 50 centimeters to implement the reflect array. So just for reference, that means 2,750 elements if you want half wavelength spacing at 1.5 gigahertz. Here's an example of what you can do with that system. In this plot, the black curve is a pattern of the unmodified reflector, or equivalently, all elements of the reflect array are short-circuited. The blue curve is what you get by choosing element states to drive a single null with no other constraints. Here we're trying to put that null at 1.75 degrees, where in the unmodified system, that would have been the peak of the second side lobe. If you assume only 1-bit control of the elements, say you can either open circuit or short circuit the patches, well, then it's quite simple to find element states that give you the desired null, and it's very deep. Now, this is using a simple algorithm to set the element states, and you see on the far left that the gain of the main lobe has changed slightly. Well, it turns out to be easy to fix that too. With a slightly more sophisticated version of the element state setting algorithm, you can implement a constrained optimization, with the constraint here being the main lobe gain, and the optimization being the null depth. Since this system involves a very large number of elements, there are a large number of degrees of freedom relative to the number of goals and constraints, so the performance can be very good. For example, the plot on the upper right shows the main lobe gain as a function of null direction, as the null is swept across the first few side lobes. Note that there's no discernible change in main lobe gain, at least not on this 5 dB scale. So this looks quite useful for satellite RFI mitigation, and we've become quite interested in this approach. Again, more details are available in the references that I'm citing on this slide. To wrap up, is it possible to observe in the presence of satellite interference without throwing away data? I think it's plausible, but of course there are limits, and we're working hard to quantify those limits. Someone's probably wondering if all this is applicable to other types of RFI, like what you get from terrestrial sources. I'm less confident that a similarly good look-through capability is possible for terrestrial RFI, and that's because terrestrial propagation is much more complicated, as I explained at the beginning of this presentation. Nevertheless, there could be a significant benefit. Here are a few words on what we're doing now on the ERS concept. First, all of this depends on knowing the unmodified antenna pattern, which probably isn't reasonable for large dishes. So there needs to be some kind of closed loop estimation where the algorithm learns the pattern as it goes along. That's a bit complicated, but we think it's possible, and we're working on it. Also, not everyone is going to be excited about the idea of modifying dishes to accommodate reflect arrays. So we've been thinking about alternatives to modifying the reflectors themselves. One obvious idea is to put the reflect arrays on panels that are attached to the rim of the reflector so that the original surface isn't disturbed. And that has some pros and cons. Another idea is that if you have a subreflector fed system, the reflect array could go on the subreflector. Again, pros and cons, and interesting to consider, and we're doing that. An idea that's come up in the course of this research is the idea of using this concept to do pattern management generally. For example, to control side lobes in a way that dynamically reduces ground noise pickup, or to correct for pattern variation with frequency. And these appear to be totally doable. I'd like to acknowledge our collaborator, Sean Hume of the University of Toronto. Sean is a reflect array expert, and he's helping us through some of the technical issues in the design of these surfaces. Concerning feed-forward coherent time domain canceling, details on all the issues I've glossed over in this presentation can be found in the PASP paper cited earlier. One thing I did not have time to mention is how time variation associated with the motion of a satellite interfere through the antenna pattern affects performance. But we've considered that. Ramanuka Sengupta has completed a master's thesis on that topic, and the news is pretty good, especially if you're willing to do some rudimentary pattern estimation concurrently with the canceling. Details on that can be found in her thesis. And work on Feedforward CTC continues. In particular, we're interested in methods that use parametric signal models as the source of the reference signal. And we're also working on the important problem of detection, which is important for intermittent signals, and especially since one would prefer that the canceller only operate when the interfering signal is present, and be idle otherwise. Future output from this project will be made available via the project website, whose URL appears at the bottom of the slide. Finally, thanks to the National Science Foundation for support via the grants indicated on this slide. That concludes this talk on techniques for observing through satellite interference. Thanks for listening.